I was primarily responsible for the Linux kernel and Nginx vulnerability injections. The way we went about selecting those was it had to have a large market share. We wanted it to be a fairly well-recognizable piece of software. The second thing was we wanted the code base to be decently large so that you could inject vulnerabilities. You didn't want them to be too concentrated. They need to be spread out across the source code. The third part was we really wanted to have unit tests, ideally. That way, when competitors submit patches, we can run this test to confirm that all the functionality still exists. So we partnered with the Linux Foundation and we began injecting vulnerabilities. And the way you trigger them with the Linux kernel is by writing C programs. We quickly encountered that LLMs, it's very hard to generate working, complex code to trigger some of these. What we quickly pivoted to was this idea of a test harness. What it does is it wraps a series of commands into a containerized, what we call a blob format. So the blob format allows 7 different commands. You can open a socket connection. You can call set sock opt. You can send a blob of data over the connection you've created. You can send a netlink packet, which is a very specific subsystem within Linux kernel. You can close a listening socket, and you can close a connected socket. These 7 function calls allow a significant attack surface for the attackers and for us to inject vulnerabilities into. However, generating this is a little difficult because it's a binary format with blob. So we also created a Python script that was generic enough to allow us to take whatever vulnerability we wrote and turn it into a blob. So here's a good example of why we decided to not require LLMs to generate source code to trigger vulnerabilities. So this is the tip-C bug that we also released as an exemplar for the teams. The amount of code and the complexity of the code required to communicate with the tip-C netlink subsystem is non-trivial. This challenge or competition isn't about code generation. It's about bug finding and patching. So that was a big influence using the blob host and the harness as opposed to requiring perfect files. The challenges that we wrote kind of fall into easy, medium, and hard. CPV1 is without a doubt relatively easy. It was injected into sockets.c, specifically the socket create function. And all it does is remove the bounds of the protocol check. You have a network, a family, and a type, and a protocol. And these are bound because what they do is they actually reference finite size structure. If you go outside the bounds, you'll cause it. And so this patch injection simply removed the checks for the bounds. So it allows you to reference outside of that, the bounds of that structure. As I mentioned before, the CPV8 is kind of a mid-range vulnerability, but it was also the exemplar CPV that we released to the teams so that they can begin understanding the format and the API that we expect. So an example of one that I would consider kind of difficult is CPV20. It was an inject into the TCP options code. So when you send a packet to a host, it'll send a SYN, and then inside of that, there are different option fields to tell how to handle this packet, what to do in various cases. But on top of that, the problem we have is we also have to ensure that the functionality is there. If teams patch out the code, you don't want it to just be gone. You want to confirm that the functionality still exists while the vulnerability doesn't. To test for this, we had to modify the code to also send back information. You send a packet, and then you get back data. So here's an example of the back and forth with the ability to confirm that the functionality is still there. You can see it sends, but then it also responds with this option 10. With this, we're able to confirm that the patch didn't remove functionality. So we selected Nginx because it had an existing project in OSS Fuzz. There was already existing infrastructure around it to do fuzzing and test harness so that we can capture when something crashes or there's a vulnerable condition that arises. And the way it works is very similar to the Linux test harness. You have a blob of data that you pass to it, and it runs it through the parsing, the handling of the functionality. We want teams to have access to the internet or the network. So the networking side of it is actually kind of stubbed out and pretend. So we trick Nginx into thinking that it's talking over the network, and it's not. Our first CPV that we went with was in this thing called the from header inside of HTTP. Nginx doesn't implement all of the HTTP spec. What I did was I browsed through the HTTP RFC, looking for functionality that exists in the RFC, so it's valid HTTP traffic, but isn't really handled by Nginx. The reason behind this is that an LLM is going to know the RFC. It's going to have been trained on the RFC, and so it will have seen this from header. Now, if I had made some other header that doesn't exist in RFC, the LLM could quickly see that, okay, I don't know what this is. I've never seen it in the RFC before. And so it kind of puts a spotlight on that code. So what I did was I added this functionality into Nginx, the handling of this from HTTP header. And it accepts an email, parses it out, and handles it. So you can see we have this addition of the from header and then how it validates it. So if an LLM is able to actually develop these patches that don't crash, fix the vulnerability itself, and conform to the programming practices of that project, it will reduce significantly the number of person hours required to fix vulnerabilities and deploy these solutions in a way to make us all much more secure.